Alrighty, yes, our speakers are ready. Our third talk of the day is a collaboration between Twitter's Chunshu Tang and Alluxio's Beinan Wang, machine learning-based SQL queries resource usage prediction. Now, Chunshu is a senior engineer on Twitter's data platform team, where he worked on developing and operating various data systems, including Presto, BigQuery, Jewett, and Graph Analytics. And he received his doctoral degree from Syracuse University, where he did research on distributed collaboration and machine learning. Beinan is our own senior software engineer at Alluxio, and he's also a committer of the PrestoDB. Prior to Alluxio, Beinan was the tech lead of Presto team in Twitter, and he built this large-scale distributed SQL system for Twitter's data platform. He has 12 years experience in working for platform optimization, distributed caching, and volume data processing. He also received his PhD in computer engineering from Syracuse University on the symbolic model checking and runtime verification for distributed systems. So you probably figured out once I just did my introduction that those two are close friends and alumni from the PhD program and colleagues supporting each other and continuing with their collaborations even when they're not in the same company anymore. So both of them are contributors to the Presto community as well as the Alluxio. So we are heavily involved with the Presto community as well. It was our engineering team and our product, as you could already tell. So this is why we love the open source community and love more collaborations. Chunshu and Beinan's talk today will introduce how Twitter's data platform leverages a machine learning-based approach in Presto and BigQuery to estimate a query utilization with 90% more accuracy. So without further ado, let's hear from Chunshu and Beinan on machine learning-based SQL query resource usage prediction.
Hi, thank you, Jasmine. Let me share my screen. Here it is. Let's see. Let me present. Hi, good morning, good afternoon, good evening, and good night. This is Chunshu Tang from Twitter. Today, Beinan Wang from Alluxio and I will give you folks introduction about, like, say, how to use a kind of a machine learning-based approach to forecast the results usage of SQL queries. Approximately, there are three sections of our presentation today. First of all, Beinan would like to give you folks a quick introduction of our Presto system about, like, say, how we organize all the Presto clusters. And then in the second part, I would like to dig a bit deeper into, like, how we use a machine learning-based approach to forecast SQL query results usage. And then finally, the last part, I want to give you folks some, like, conclusions and takeaways that what we have learned from our experience. So first of all, let's welcome Beinan to talk about, like, the overview of the Presto system.
Okay, thank you, Chunshu. Yeah, let's go to the next page. I will give an overview of the Presto system and also the router and the predictors. Yeah. The Presto, I think it's one of the most popular SQL engine for the analytical workload. And I think nowadays, most, the data scientists or engineers, they love to use Presto for multiple use cases. Maybe some query, maybe it's tiny, it's very small, it can be finished in a couple of seconds, but some of them might be very huge. It can be maybe finished in a couple of hours or a couple of days, something like the ETL jobs. Yeah. So let's say that the Presto actually are handling multiple workload, and also they will use the very different resource for each query. Let's go to the next page. Yes, and as I said, the Presto actually is a popular query engine. We know quite a few giant internet companies are using this for better scalability and also for the better resource usage. They may set up multiple Presto clusters, but by doing so, they also need a router, Presto router, to be set up in front of these Presto clusters. And the router will distribute the load, or we can say the query, to the Presto cluster. But the issue is we found the utilization for each cluster might be not balanced because the router may based on the round robin or maybe based on the table name, something like Meta did in their private cluster. But some cluster might be much more busy than the others, right? So we may see the latency increase. We may see the some cluster become very unstable. Okay, let's go to the next page. We involved a query predictor to working with the router. So the router will, based on the result of the query predictor, to decide which Presto cluster we should go. And this query predictor will do an estimate of this SQL, and it will give you the CPU time and the memory usage. So the router can just based on this kind of information to do the routing. And also this predictor can also integrate with the BI tools, something like Zeppelin. So when the data scientist construct a query, they can get the estimation of the running time of this query immediately. Then they can decide maybe something wrong, maybe it's okay. Maybe they can just cancel the query based on the result to save some resource. And also because now we are deploying the Presto cluster into the cloud, so we have the ability to scale up and scale down on the Kubernetes. So we can also, based on the result of the predictor, to make a decision when we should scale up the Presto cluster to get more compute resource. Also, we can make a decision for when we should scale down the Presto cluster to save the cost. Actually, the predictor is not something new. It's already have been there for decades, but the existing DBMS approach, they are based on the query plan. It's quite heavy, but our predictor is something different. So I will leave it to Chunxu to show the magic of our AI predictors. Thank you, Chunxu.
Thank you, Beinan. Let's jump to the second part of the presentation today, where I want to talk about, how we use machine learning techniques to help us to predict the result utilization of a SQL query. So here is the overall design of our system here. The SQL federation system is just as what Beinan has explained and talked about. And here we want to add another system, which is a query cost prediction system. And it has a few components, which we will talk a bit more about them in this slide. So here, first of all, for a machine learning job, usually we need some data for training, right? So for us, the training data is some request logs. For each SQL query process in the Presto SQL engine, it will generate a piece of request log, like say, it may include, say, the SQL query itself, the LDAP of the query, the service account of this query, the query plan generated, the CPU time, and the memory usage of this query, etc. So for us, what we have observed is that the records in the latest 3 months are a good indicator for our training job. And for us, there are around 1.2 million records in the latest 3 months for the request logs. And then we have a training cluster. There are 3 major steps in the training cluster. It will be used for data cleaning and discretization. And then we'll do some feature engineering to extract some features from the SQL queries. And then we'll do some model training job. For the model training, we train 2 specific models. One is to forecast the CPU time of SQL queries, and the other is to predict the peak memory bytes of SQL queries. And then we also have a model repository component, because after the model training, usually we should store the models into a central repository for storage and for the further serving. So for us, we can store the models on HDFS or GCS buckets, which are usually kind of archival storage. And then when we have trained all the models, stored them, we want to serve them in the production environment with some online real-time traffic. So to achieve that, we have set up a serving cluster to serve incoming SQL requests for the prediction of the resource usages. Yeah. And now I want to give you folks a deeper description into the steps, how we set up the machine learning pipeline. So the first step is about data pre-processing here. With the data set, the training data set, which are from like raw logs of Presto, we'll do the data discretization first, which we will categorize the data into different buckets, into different types. And then we'll also do some data cleaning here. So one thing that we want to mention is about like how we bucketize the data, because the case for CPU time and peak memory bytes is that this type of data is continuous data. But to achieve the prediction of continuous data, we usually consider it as a regression task. But for us, we transform it into a classification task by putting the CPU time and peak memory bytes into a few buckets here. There are two major reasons that lead to our decision about this design. The first of all is that we find customers don't care much about the accurately predicted value. Say I am a customer that I want to know approximately how many memory bytes will be consumed by of my query. I may not care about whether it will consume, like say, 1 GB or 1 GB and 1 MB. That's accurate, right? So generally, I want to know whether this is a really heavy query or it will be a lightweight query, right? And also the similar for query scheduling and scaling of our Presto clusters. That's usually for this kind of mechanism, we don't have to know a very accurately predicted value. Generally, we want to know approximately which range the query may fall into. Like say whether this is a lightweight query or this is a medium resource consuming query, or this will be a heavy query, right? So that's about like how we do some data cleaning and pre-processing there. And the next step with the cleaned data sets, we want to do some feature engineering from it, where we want to extract useful features from the data sets. First of all, we split the clean data set into a training data set and a testing data set. Then for the feature engineering, we applied kind of natural language processing techniques, NLP techniques, like word frequency and TF-IDF, which represents term frequency inverse the document frequency. Those two techniques are pretty popular techniques used in the natural language processing domain, that it will help us to extract some features from the words of the SQL queries. And then we'll do some model training and evaluation. For us, we did some experiments of 3 different classification algorithms, random forest, XGBoost, and logistic regression. And with the models, we also evaluate them from different dimensions, from different metrics. And how we evaluate that? First of all, the first metric that we use is the overall accuracy. And as we use the 3 different classification algorithms with 2 different feature engineering approaches, so in total, we have 6 combinations. And we report the overall accuracy of the CPU model and the memory model for all the 6 combinations here. And what we have found of the results is that the XGBoost plus TF-IDF seems to give us a higher performance over other approaches on both the CPU model and the memory model here. You see, for this approach, the accuracy of the CPU model is almost 98%, and the accuracy of the memory model is 97%. But another thing that I want to mention here is that accuracy is only one metric that is used to evaluate models, but it is not the only one, especially considering our case. Let's go back to this kind of a slide, and you folks could see that they're kind of imbalanced classes here, especially for the CPU time range. So it means that the overall accuracy here may give us some misunderstanding to evaluate the model performance. So to help that, what we also want to consider is that we evaluate the precision and recall of each range for both the CPU model and the memory model here. The precision means that how many selected elements are relevant, and recall means that how many relevant are correctly selected. So we evaluate precision and recall for all the ranges here for the XGBoost plus TF-IDF approach. And we also observe that this kind of approach achieved high performance on all these fields listed in the two tables here. With after we train the models, we evaluate them. Another step is that we need to serve them into an online production environment. And also another very important thing is that we need to continuously monitor the model performance, because as the time goes, usually we'll see model decay, usually due to like say some other factors like concept drift or data drift. We have served the models into Twitter's online production environment, and we also see such kind of a scenario that say take the figure A, the sub figure A here as an example. We find that as the time goes, the model accuracy will gradually drops. Yeah. So a very important thing is that we need to do some remediation to help to let the models to regain the high performance. And the approach we have used is it's a very straightforward approach, that is to retrain the models. We set up some threshold for the model precision and recall. And when the threshold is reached, we will retrain the models and reserve them in the online production environment. And for example, here, still take the figures, a subfigure A as an example. Say we retrain the model at the week 3, and you folks can see that after the retraining, the CPU time and the memory model regain the high performance for the overall model accuracy here. Okay. And another thing that I want to share with the whole open source community is that this project now is completely open sourced. Previously, it is tightly coupled with some Twitter specific tech stacks. But now we have rewritten the whole code base and open sourced the project and contributed back to the Presto community. So here is the name of the project is called Presto Query Predictor, and it has been organized into the PrestoDB repository. And we also have necessary docs related to how to use it and like say how to deploy it in your production environment. And after we share all the things, for now, most of the things we have shared is just on Presto, right? So maybe some customers may ask, like say, could we apply this kind of approach to other query systems, or is it just Presto specific? Luckily, from our experiments, what we can say is that it could be generalized to other query systems, and we have already done so. Here is another thing we have done is that to generalize this approach to BigQuery. For BigQuery, it's also a data warehouse. It is a data warehouse provided by Google Cloud. It has a bit differences between from Presto. Like say for BigQuery, usually we don't directly use something like CPU time, but we use a term called slot. And the BigQuery slot is a virtual CPU used by BigQuery to execute the corresponding SQL queries. So for each piece of query log generated from BigQuery, it has a corresponding field named total slot millisecond. So what we have done is that we generalize this approach to predict the total slot time for each SQL query. And we put them into two categories. One is 0 to 1 hour, and the other is larger than 1 hour. And we still use the XGBoost plus TF-IDF approach onto it to predict the total slot time of each SQL query. And the overall accuracy from our experiments can achieve as high as around like 92% here. And we also report the precision and recall of each range, which has been listed into the table on this slide. Yeah. So from this, what we can see is that this kind of approach not just works very well on Presto, but it could be also be generalized to other query systems to help to predict some resource usage of SQL queries. Okay, so in the last section, we want to share some conclusions and takeaways, which I think this is a very important section that because I believe that when you folks join this seminar, you may want to learn about, like, say, what kind of thing that you could reuse in your production environment. So here are some things that we want to share. The very first thing is that we find that machine learning can be useful to solve some infrastructure related problems. Like, say, for the resource usage prediction of SQL queries, we find that when we even using some basic models, machine learning models, can give us quite good results. You see, what the approaches that we have used is basically some very popular classification algorithms like XGBoost, the random forest, the JC regression. We didn't apply many complicated like deep learning techniques, like some neural networks, or like, say, some transfer learning, transformers for feature engineering, not at all. But even this kind of basic machine learning techniques can help us to give us some very good results. The second point is that for a machine learning job, usually we need to have some data for training, right? And what we have found is that for infrastructure related problems, we usually have logs, and those logs are pretty reliable starting points for some machine learning experiments. And we can use that logs as a kind of input data for our machine learning pipelines. And the last point is that we also need to be careful when evaluating our models, because there are many metrics that we can use to evaluate them. Accuracy, like, say, the overall accuracy is just the one useful metric. There are many other metrics that we may also use to help us to comprehensively evaluate our models, like precision, recall, F1 score, etc. And there are also some future work that we are doing, like, say, for example, we want to apply a more sophisticated bucketizing approach to our feature engineering. We also would like to apply some more state-of-art classification approaches. And also, you folks have seen that there is some model decay happening when we serve it online. We also want to optimize the model decay here to help us to reduce the model decay. Also, there's another very important thing we are doing is about, like, say, the model interpretation. Because when we apply machine learning to infrastructure problems, we also wanted to interpret the models to see why they could achieve so good results. In that case, it can also help us to gain insights of our infrastructure systems. Yeah, so that's mostly what Beinan and I would like to talk about today. And here is a Q&A session. If you folks want to know anything, feel free to let us know. Or you can also always find us in the Alluxio Slack channel or the PrestoDB Slack channel. Okay.
Okay. Thank you, Chenshu. Appreciate it. I'm gonna reroute one of the quick questions from the Zoom first before and other ones. So Robert from the Zoom asked, how does the Presto router use the predictions to optimize query scheduling?
Yes, that's a good point. Let us go back to this the page 5, the slide 5. Here, you folks could see that we have the router service and we have the query cost prediction serving cluster, right? So in that case, the router can use the resource usage predicted by the serving cluster and use that result to schedule queries across all the Presto clusters. Yeah, so that's right, that's correct. That's what we are doing now in Twitter. Yeah.
Cool. Robert, if hopefully we answer your question. If not, feel free to have a follow-up. We do have another one. So from Diego on Zoom, is routing the only product you have to build in a model?
The case is that when we have the models, and there are multiple usages of these models at Twitter's production environment. One use case is that we combine the prediction service and the router together to help the router to route requests across different clusters. And at Twitter, we have also encapsulate the serving mechanism with other like BI tools and notebook tools like Zeppelin. So in that case, you folks can see here, for example, for the second point, our customer want to know the resource consumption estimation of their queries. So for example, when we combine the serving mechanism and the notebook service, say Zeppelin together, then all the Zeppelin users, before they ran their SQL queries, they can just click a button there to get estimation of the resource consumption of their SQL queries, even before their queries are really executed in Presto. Yeah, so that's also something that we have done. Another thing that point here is about elastic scaling. That's also what we are doing now in Twitter. That for this use case is that the workload of the clusters at Twitter is not very stable. Sometimes some clusters may be very busy, like especially during the business hours. But say after hours, it may be idle there. So we want to do some elastic scaling with all the prediction results. So when we predict that there are some like very heavy queries will be crowded in this cluster, we will quickly scaling up the cluster on the Kubernetes environment. And when we find that we don't have many queries running at this moment, we'll scale down the cluster. So in general, there are a few use cases of the prediction results. Yeah.
Cool. I think that was so Robert had another question. If the prediction indicates a heavy query, how does the router handle that? How does it send the query to the cluster that has the most resources available?
Oh yeah, that's a really good point. Yeah, thanks for the question. So I think I can give you folks a bit more insight regarding it, because I think that's a really interesting open question about, say, when we have this prediction results, how we want to use that kind of results to help us scheduling all the queries across clusters. And the case is that in Twitter, we have tried a few different approaches for that. For example, one approach we have tried is that we don't want the heavy queries to have much impact on some lightweight queries. So in that case, we set up a specific cluster with some more resources as an independent cluster, especially to serve some very large, heavy, like resource-consuming queries. So let's go back to this slide. So when the query comes into the router and the router gets the estimate of the resource usage of this SQL query and say, oh, this is a pretty heavy query. In that case, it will route the query into that specific cluster with some more compute resources and especially designed for the heavy queries. So that's exactly what we have tried and what we have experimented at Twitter. Yeah.
Cool. Awesome. Well, I did have my questions before someone else hijacked it. So I want to know if the method of predicting resource usage also applicable for online adjustment of resource allocation.
Yes. That's also kind of saying, like, say, I mentioned as the elastic scaling. So when the queries come into the router service here, we'll see, like, say, what are the queries that will be sent to the clusters. If, like, say, we see there are many heavy queries come into the router, we'll scale up the clusters to handle those more like resource-consuming queries. Yes, so that's correct. That's what the query resource prediction can help with. That when we see, like, say, more resource-consuming queries, we can scale up the clusters. When we see there are fewer and fewer queries, and then we can still scale down the clusters. Yeah, hope my answer is helpful. Yeah.
Yeah. Oh, there is another one from
Mhm.
Peng Li on Zoom. What features are used to train the query prediction model?
Yeah, that's a good point. Feature engineering is usually one of the most important part in the machine learning pipelines, right? And so here our approach, and let's go back to this slide. This approach, what the features that we have extracted from SQL queries is just some natural language processing features. So we don't, different from previous existing like database approaches for like for some prediction. In our approach, we don't use query plans. So in that case, our approach is SQL engine agnostic. So it means that it cares nothing about the query plan, but it's just the text of the SQL queries themselves. There are two approaches that we have used, all from natural language processing. One is word frequency, that we use the frequency of each word to represent the word. And another is TF-IDF, where we use this TF-IDF to represent each word of a SQL query. So in that case, we can generate a vector of numbers of each sentence, and then we can feed the sentence, so this kind of numbers, into different classification algorithms to train the models. Yeah, so that's what we have used for our models.
Cool. I think I've addressed Robert's question already. Okay.
I think I can just add one quick point here. And actually, we also published a paper in last year about all the details that we have done about this project. So I think maybe in the final slide I shared with the whole community, we can attach the link of the paper here in this page, so you folks can have more details about like the work that we have done. Yeah.
Oh yeah, definitely. You can update it, then it will, when we share that with the community, we can do that too. And then you can also type, if you want to, if you have that link, we can also just post them live on the Slack channel. I don't mind either way, whichever point people to the same. Sure. Yeah. So one more, is there any difference in prediction when the Presto cluster is busy or when it's idle?
Yes, that's I think that's also a good part, a very good part of our design. That is, our design is just based on the SQL queries themselves. So we don't care about any like query plans, any specific SQL engines. And another thing is that we use the CPU time and peak memory bytes for each SQL query. So in that case, mostly, no matter what is the hardware configuration is, the SQL queries, the CPU time and peak memory bytes consumption remain stable and remain the same. Yeah, so that's what we have been doing.
Awesome. Thank you. You'll be manning all the Q&A. Beinan's having a good time. Well, good seeing both of you. Well, I'll see you next time, and then we're going to move on to the next one. Thank you, Chunxi.
Yeah, thank you.
Thank you, Beinan.
Have a good day.
Mm-hmm.